Okay, so today what we're doing is we are relating the first derivative, second derivative, and third derivative. And we're going to talk about the first derivative test and the second derivative test, and then also what the second derivative means for us. So we're going to do all this within our allotted amount of time, hopefully within 30 minutes or less, or it's free. So let's get started. So we're going to relate the derivatives. So f to f prime to f double prime. How are they related? Going forward, not backwards, going forwards, okay, today. So we're given the idea that the derivative tells us the change of something, which is great. So when something changes from a positive to a negative, we have to cross through what number? To change from a positive number to a negative number, we always have to, thank you, always have to cross through zero. And that's always a thing. Think, if you're on the third floor and you get to the basement, you always have to cross to the ground floor. There's no way for you to teleport across that. So we have something special, and we talked about critical points. And critical points are pretty much when graphs look like this, when we have a point that looks like this, or a point that doesn't have a derivative. So f prime is equal to 0, or f prime does not exist, or undefined. Does not exist, or undefined. Okay, and these points are special. They are not necessarily a min or max, but they are warning, 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 warning. Okay, we got a problem here. Now, if I give you a problem that looks like 1 over x, when you take the derivative of this, x to the negative 1, let's take the derivative of this, f prime would be negative x to negative 2, 1 over x squared, right? We realize we don't have a derivative at x is 0, right? But we also didn't have a value at x equals to 0 either here. So it doesn't negate the fact that we still have a problem here, and we know that this graph doesn't have a derivative. Oops, wrong way. At 0. Does it mean we have a max or min there? No, it just means be aware we have a problem there. Now we talked about the mean value theorem and all that stuff, and we had rules that stuff had to be continuous and differentiable. And in this case, for 1 over x, it's not continuous and it's not differentiable. It's nothing about it. So we can't use any of our rules on this. But we did have a our mean value theorem, not mean value theorem. We had our rule that said we have to have a max and min on a closed interval that's continuous. And this isn't continuous, so we don't have a max. So let's go back to critical points of what they mean. So critical points are when we have, again, a slope that's 0, that's what it looks like, or it doesn't exist, okay, a little sharp corner. And that's something that we learned in pre-calculus also. Now, there's some characteristics of when something is a max and something is a min by looking just at the slope. And we talked about this again before. So let's look at the slope, looking at slopes. So if I give you a maximum, oops, the slope here is 0, and we have a critical point there. But please look at the slope. F prime is positive to negative. So if the slope changes from a positive to negative to negative, we have a max. And this is a local max or a relative max, because we don't know, oh, this could also be an absolute max, but we have to compare it to everyone. But at least for sure, at least it's a local max or relative max. Remember, these are the same words, local or relative. Does this work when it's undefined? Well, let me again draw you the same point. This is undefined, right? Or it does not exist, but the slope still goes from a positive to negative. So as long as our sign changes from a positive to negative, we have a max. How about if we go the other way? So this is still a max, because we go from a positive to negative. What if I go the other way? this slope is 0 here on our graph is pointed. This does not exist. These are f primes. These are our derivatives. The slope changes from negative to positive. Negative to positive. We have for sure a minimum. Oops. So things that we want to be aware of. So we automatically know it. So a dumb example of this is us just doing a quadratic. If I say f of x equals to x squared plus 6x plus 8, we want to see if we have a critical point, take the derivative, make this equal to 0. We know we have x at -3 is a 0 there. So we have a critical point. But the problem is we don't know it's a max or min yet. Sure, you might say, Mr. Coe, x squared is going up, facing upwards, so that's a minimum. You could do that. And that's actually going to be part of our second derivative test. But right now, draw a line, simple line. Don't draw the arrows if you don't want. X is -3, and I was right, the derivative on top. So f prime is 0. So we know there's a special something happening there. And if we say on the left side, so pick a number that's less than -3, -4. And if I plug in -4 into my slope equation without doing any math, is that going to be negative or positive? That feels like negative, right? If I plug in -5, that's going to be negative because 2 times -4 is bigger or more negative than 6. If I plug in -5, 2 times -5 is more negative than 6. So we are always going to be negative on the left side. Some teachers would teach it as they'll just draw a bunch of negative signs everywhere here. And what this means is that the slope is downtrending. It's going down. On the right side, if I plug in a number, let's say -2, you know what? Please don't plug in -2. Plug in 0. 0 is always super easy to plug in. If you can plug in 0, choose 0. Choose 0, everyone. Now, if I plug in 0, that's going to be positive. And I can guarantee you it's going to be rising on the right side. So if the trend goes from negative to positive, or in my robot mode, -0 positive, we have a minimum here. We have to have a minimum. So did we have a sign change from a negative to positive? Yes, and that's actually the rule. If you have a minimum, you have to have a sign change. There's no other possibility. You can't say, oh, it looks negative. The AP exam is expecting you to say there's a change in sign from a negative to positive. And that's it. That's the first derivative test. That idea is seeing a sign change from negative to positive. Okay. So minimum at, let's say minimum at x equals to -3. F prime changes from negative to positive. Right? That's the logic behind it. Now, if I give you guys a fun year problem, I'm gonna just take the book's example because it's here. If I give you 3x squared minus 12 equals 0. Actually, you know what? Yeah, that's just, no, oops, sorry. Book's problem is this, f prime. Okay, that's already the derivative. This is already the derivative, folks. They did the work for us. Right? And the original problem could be something like x cubed minus 12x or something, right? Some graph like that, plus c. That's the original ORG. So let's say they give us this problem. So they did all the work for us. I'm going to factor out the 3 because I want to find the zeros. X squared minus 4 equals 0. So we can factor this to be x plus 2, x minus 2. So we have critical points at -2 and 2. We do not know which is the max and which is the minimum. We don't know. That's okay. I'm going to draw a little sign chart here, and -2 and 2. I'm going to write zeros on top of that just to remind me that these are critical points. Now, you know what? If you guys know what x cubed is, x cubed we know is going to go up on the right and down on the left. Okay, but be careful. Reading from left to right, this is a positive slope and a positive slope also. Just FYI on that, okay? If you know this already. But I want to show you guys that using our calculus here, our basic calculus skills, we don't need to remember that. Of course, knowing that saves us time, but we don't need to know that because the slope is going to be defined by us just plugging in values. Pick a number bigger than 2. That's pick 3. Now, when I pick 3, please watch here. Everyone has to pay attention. Don't do the math. Don't do the math. 3 is positive. Is 3 plus 2 positive or negative? Don't just think about it. That's positive, right? Positive times positive. 3 minus 2. Don't do the math. That's positive. What's a positive times positive times positive? That's a positive that we want to have. And if you pick any number past 2, bigger than 2, this will always be positive. Bigger than 2, isn't 2 bigger than -2? That will force it to still be positive. No matter what numbers we pick, they'll always be positive. Let's pick a number on the left. Let's do -3. Now, -3 is just an option. You could pick -10 if you want. But if I pick anything, let's say pick -3, isn't that more negative than 2 here? So no matter what number I pick now on the left side will be bigger or more negative than a positive 2. So we know this is going to be negative. Negative, negative is going to be negative. And then this is a positive. Negative, negative, positive will still stay positive. So no matter what number I pick, this will be positive. And so you can do these sign charts very quickly. And what happens between -2 and 2? Easy number, 0. And this is where, we kind of make that critical decision. If I pick a number 0, isn't 0 always going to be bigger? Sorry, isn't 2 always going to be bigger than 0? This will always be positive. So within this space here, no matter what number I pick, this will always be positive. In the space here, no matter what I pick, this will always be negative. And the 3 is a positive. Positive, positive, negative, we always will be negative in that interior space. Now again, you could just, if you want, teachers teach us as plus, 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 minus, 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 because no matter what numbers you plug in, you're still going to end up with that sign. But the cool thing now is that we can tell which is our local mix and local man. Local mins and local maxes. So the sign says positive to negative. That's a max. And negative slope to positive slope, that's a, whoops, yeah, this is a min. And we know where these minimums and maximums occur. Now, if you want to actually figure out the value, you plug the x value into your original function, and this will tell you the actual x and y point. The max happens at 2 comma blank. The min happens at 2 comma blank. You can fill that out back into the original f problem, because the f is our position, tells us where we're at. So,
Mr. Ko, I have a question.
Yep.
So, because they didn't give us the original equation, and you just have that c at the end, then how would we know what the y value is?
So, when we actually learn how to do integrals, they will give us a point. They'll tell us when x and y is like 1 comma 2. And that's when you can plug in the x and the y and solve for c. But till then, it could be anywhere. Because that example is actually from Algebra 1. If I told you the slope of the graph is 2 over 3, what's the original problem? I don't know. 2 over 3 is like anywhere you want. Till you give me an actual point, we do not lock down the graph. And that's something about going backwards integration. When you take the derivative, you lose information. You lose position. Like if I tell you I'm driving at 100 miles an hour, it doesn't tell me where I'm at. It doesn't tell me where I started. So going backwards. So we do not know until they give us more information. Good question. Okay. Now, the second part of this is F double prime gives us concavity. And concavity is another way of thinking about acceleration. So if F prime is change, when you're driving a car, your speed tells you how fast you're changing, like miles per hour. So if F is my position, the derivative of F, let me write this down. F is position. F prime is change. So the change of position is velocity, such as miles per hour, right? That's a change, and that's velocity. And then F double prime is acceleration. And acceleration is the change in velocity. So for instance, when you're driving at 20 miles an hour, because you guys don't drive very fast, right? And a dog runs into the street, you hit the brakes. That's a deceleration. That's a change in your velocity. If you are driving at 60 miles an hour and you run into a wall, you change in velocity because you change in acceleration. You decelerated at a point where your brain is now mush. So these are all related, and these are also called kinematics, kinematic equations. And that's like another thing. Okay. So here's something kind of cool. So if F double prime is greater than 0, we are concave up. And if F double prime is less than 0, we are concave down. And what happens is this tells you, is the object accelerating or decelerating? Now let's take something that we know in general. Like on planet Earth, when I throw a ball in the air, it goes up and it comes down, right? It forms a nice parabola. No matter what part of the Earth, you throw the ball up, it'll come back down in this nice parabola. Now, let me show you something. This is concave down, right? It's facing downward. Now, concavity, the idea is which way is it opening? Is it open up or down? And concave down means it's facing downward. That's the idea of concave down. But also, if you guys have done physics problems before, gravity is acting at this at a negative 9.8 meters per second squared. Now, why do we say negative? Is because when I throw a ball up in the air, I'm giving it a positive velocity because it's gaining altitude, you could say. It's gaining value. And what does gravity do to my velocity? It starts subtracting from it. It starts sucking the life out of it. It's sucking the energy out of it. If you guys are taking a physics class, that's the idea. So if I give you a problem that says, I say f of x is equal to negative x squared plus 6x plus 8. Okay, we know this is a parabola facing downward. Okay, that's a hint. And if I take the first derivative, this gives me negative 2x plus 6. Great, that's awesome. Wonderful, thank you very much. And then, so we know where the change could happen. So at x equals to positive 3, we have a change in sign. So let's just do our little sign chart. So at 3, 0, if I plug in a number bigger than 3, 4, 5, 6, the derivative would be negative. 0, the derivative would be positive. Okay, is everyone cool with that? F prime would be positive on the left side of 3, and it would be negative on the right side of 3. Everyone has to lock into that and be cool with that. So that's the change. My slope is up, 0, down. It's already looking like a downward facing parabola. a couple things we can lock in now. Since I know the original function, if I plug in 3 here, negative 3 squared plus 6 times 3 plus 8. This is negative 9 plus 18 plus 8. That's 26 minus 9. That's 19. So we know we said this was a max because we increased, decrease. We have a max at 3 comma 19. I think that's right. I did the math right, hopefully. Okay, all right, moving on. Wait, whoops, not 19, dang it. This is 20, so 17, right? All right. Yeah, 17, 3 comma 17. So we know where the max happens, and this is all from our first rule. Okay, our first derivative test helped us find that this was a critical point. Critical point led to a change in slope from positive to negative, so we have a maximum. All right, now the next part is, you could actually skip this. This actually takes a lot of time, doesn't it? This takes a little bit of time. So instead, if I took my second derivative, you see that the concavity will always be facing downward. So we know the graph is always facing downward. So here's something kind of cool. We found a critical point at 3, and then we know that the graph is facing downward. What do you think this is, a max or min? If it's facing downward, we know our critical point is a max. So because f prime, double prime, is less than 0, well, let's draw this with less words, is negative, right? This implies concave down at critical point x equals to 3. Hey, if we know it's concave down, we have a, concave down at 3. We know x at 3 is a max. Now it's a little counterintuitive, because if I'm saying concave down, that's negative, why would that be a maximum? So use your hand and face downward, and you'll see the apex of that, that's a maximum. That's your critical point. If I'm facing up, that's a loser, right? You're the lowest score in the class. That's a minimum. So concavity can tell me if that critical point is a max or minimum. Okay. Now, going back to the idea of me throwing a ball up in the air, if you notice that the acceleration here is constantly negative, that means when I throw a ball in the air, the energy is being sucked out of it. It's decelerating. So at the point up here, the velocity becomes 0, right? See how the velocity became 0? And then the velocity starts to decrease. Right here, velocity starts to decrease. So they're all, unfortunately, very related to each other. And when you take physics in college, or you take AP physics, it's based on a calculus standpoint, where they're all related: position, velocity, and acceleration. Okay, so let's do another problem here. So if I give you a problem, let's do f of x is equal to x cubed plus 4x squared plus 3x. Okay, I'm just making this up. I want us to find our critical points, or find min and maxes using f double prime. Okay, we're going to find the min and maxes not using our first derivative test, not using our sign chart, but we're going to jump to the concavity You can tell me if it's a min or max just by looking at the concavity. So let's go take the derivative, 1. This will be 3x plus squared plus 8x plus 3. Darn it, let me make your lives a little easier because we can't factor that. Erase the 3x. Erase the 3x. Trust me, you'll thank me later. Hey, erase the 3x. Make the problem easier. Right? Now we're going to make this go to 0. Go ahead and tell me the zeros of this graph. Those are critical points. So we still have to find critical points. That took you a lot of work, right? Being sarcastic here. The other one, we would have to have done quadratic formula. So I said, forget it, a mistake. And now we're gonna take the second derivative here. That's gonna become 6x plus 8. Now, we're gonna solve for 0 here. And because that's gonna give us a new feature, okay? That's gonna be a new feature. So x is equal to negative 8 over 6, which reduces to negative 4 over 3, sorry. So let's draw negative 4 over 3. And I want us to place our two little bits of two critical points here. So 0 would be over here, and negative 8 over 3 would be there. So this is f double prime, okay? We have 0 there. So on the right and left side, you tell me, on the right side of this, over here, would this be positive or negative according to my second derivative? Remember, don't think too much about it.
Positive.
Positive, yeah. If I pick any number 0, isn't this going to be positive already? If I pick a fat negative number, this will be negative. Look how much work we did. Now, here's what you want to notice. A positive concavity means this is going up, right? So what do you think 0 is going to be, a max or a min?
Min.
Min. Good job. And since this is downward facing, concavity is negative, this guy's going to be a max. So we can automatically tell if something's a min or maximum, looking at our second derivative. Now, here's something else I need to say. We have a special point here now. When this equals to 0, when f double prime equal to 0, and there's a change in sign, let me actually write this over here. F double prime equals to 0, and change in sign. This is called a point of inflection. You know that point in your life at Christmas break, and you're like, oh man, this has been a nice break. And you go, oh crap, I haven't done any of my work. I'm so screwed. It's due tomorrow. That's a point of inflection. That's when all the highs become all the crap and lows. And our point of inflection is a change in concavity. Now, let me show you a bigger idea of what this means. Let's say if the graph goes something like this, okay? Big picture idea, okay? So we have concave down, and then concave up. Concave down and concave up. So the point of inflection is someplace here where you've all of a sudden stopped decreasing and started to increase. Where the concavity changes from a positive to negative or negative to positive. Now, you don't have a point of inflection unless there is a change in sign. If you go from a negative to negative, like you go from sad to sad, there's no point of inflection. It's more like just my whole life of depression. Then you go from happy to sad, that is a change. That's a point of inflection, right? We don't change it from happy to happy. Oh, I went to Disneyland. I was so happy. And I just became happier. Right? The point of inflection is when you crash from all those freaking hot dogs and turkey drumsticks, or when you realize the lines are 3 hours long. Sorry, no hate there. So the cool thing is that here, let me show you this as a car, right? I enter my drive at 100 miles an hour, right? Zoom, zzz, but I'm slowing down. I'm slowing down till 0. So what happens? My velocity here is now 0. Oh, poor baby. And then I'm heading backwards. I'm driving in a negative direction, right? Negative direction, negative direction. And at some point, I'm super like negative 200 now. Whoops. I'm like negative 100 now. Okay. So here's the image of a bullet going in the air. You've heard this rumor where if you fire a gun in the air, the speed the bullet travels up is the same speed as it comes down. And that's true. Once you take away some air resistance, when you fire a bullet in the air, whatever speed it starts off with is sucked away by gravity. So it eventually hits a maximum value of 0, or so whatever height, but the velocity stops for just a moment, like you throwing a ball in the air. But right afterward, doesn't gravity start pulling down the bullet? Pulling down the bullet, and it's gonna fly at the same time as it went up. That means the velocity is being increased because of gravity. It's just getting pulled and pulled and pulled and pulled and pulled and pulled. By the time it hits the ground, it'll be negative 100 or negative whatever speed. And then, but how do I slow it down? Imagine if it hits water. Doesn't that slow down the bullet? And that's that change in inflection, where then I change it in a different manner. But then the problem is I have to be pushing air up. So we can think of this as a feather falling, and then me blowing it back up. And then all of a sudden changes speed and starts heading in the other direction. So this point of inflection is a change in acceleration. Another way of looking at this is if you guys have started driving or been in a car where someone is learning to drive, and you can feel when they step on the gas, step on the brake, step on the gas, step on the brake, you get whiplash. That's this idea of acceleration and deceleration. And there's a point of inflection where you're just like, oh, just at peace for just a moment before they hit the brakes. So this point of inflection is important for us. But the cool thing is that within this point of inflection, we can have maxes and mins at where? The critical points. So the ways of using our second derivative test is that 1, find our critical points. Okay, first step, find the critical points. These are special to us no matter what. Step 2, tell me concavity. If it's concave down, use your hand. If you point a cup facing down, we have a maximum value there. You guys look at the screen, right? If it's concave up, the critical point will be a minimum. And these are just things that we flow from logic, okay? If you guys remember the graph, let's see if we can do this one. Sine x over x. Guys remember this ugly little turd? In the graph for sine x over x, looks something like this, right? And we could say before the limit as x approaches 0, it doesn't exist, but it would be like 1. Actually, you know what? This graph doesn't work. Because why can't we do this rule? Is this continuous or not continuous? It's not continuous, right? Because you cannot plug in 0 here. Let's look at another graph. This
But Mr. Ko, when you find the zeros of this on the second derivative, that gives you the point of inflection?
Only if it changes sign. If it doesn't change sign, it means jack. A point of inflection is just a fancy word that the acceleration has changed from a positive to negative, that there is a change. Okay, so the book has a fancy problem. Let's use this one because it's here. 100% left. Oh no, we're out of time. Oh gosh, we went overtime. Oh shit. Okay. All right. Besides that, I think this is all you need for this homework today, right? And then, FYI, F prime, that's change, right? If change is positive, that means you're increasing. If F prime is negative, that means you're decreasing. Just another couple keywords to realize, right? If your velocity is positive, that means you're increasing. If your velocity is negative, that means you're decreasing. These are just play on words. Okay. You can also look at 5.3 in your textbook, which is pretty much where all the materials from. Thank gosh, time just flies.
When you're having fun.
Oh yeah, thanks. Thanks for adding that right at the end before I stop the video.